Rational functions. A rational function is a function that can be written in the form of f of x is equal to ax over bx, where the numerator ax and the denominator bx are both rational expressions. Also, we need to consider we have a non-permissible value that bx must never be equal to 0. That is, our denominator can't be equal to 0. So really, what is a rational function? A rational function is a function in which the numerator or the denominator has a polynomial. For example, like this. That could be a rational function. Now, let us look at the graph of various rational functions. So I'm going to talk about the first graph. First graph is absolutely crazy. I don't know how anybody can expect me to draw that. Second graph sort of looks like the first graph, but it's still a rational function. The third graph looks nothing like the first or second graph, but it is still a rational function. All of these are rational functions. What can be expected in rational functions? Well, your graphs will have an unusual unusual characteristics to it. And I'm just going to say that sometimes these rational functions have almost guidelines that you can draw to help you graph them. And if you look for these guidelines, either horizontal or vertical, nearly every, not all, rational functions will have these guidelines that we need to draw. Sometimes they have vertical, sometimes they have horizontal, and sometimes they have neither, or both. So today we're going to be looking at rational functions. An interesting component of rational functions are asymptotes. From a simpler perspective, an asymptote, what we've seen above, can be thought of as guidelines upon which a function follows. But looking at it from a different perspective, asymptotes describe the behavior of the function. So asymptotes describe the behavior of the function and are going to be incredibly important. Because if you know how the behavior of a function, likely you'll know where it will be. Definitions. So an asymptote is these sort of guidelines, and we're going to talk about the horizontal guidelines. A horizontal asymptote. The value of the function f of x approaches, now this little arrow, you can say approaches. The value of the function approaches a constant c as x gets infinitely large. Now I'm just going to revise this as x gets infinitely large, positive or negative. Note, a horizontal asymptote is a horizontal line, and thus has an equation of y is equal to c, where c is a constant. Another perspective, a horizontal asymptote can be thought of as the left-hand and right-hand side of the behavior of a graph. Now, I'm just going to scroll up a bit. I'm going to take a look at graph number 1. What we see is that I have a horizontal asymptote here along this line. This line will have the equation y is equal to 0. It's important to note that if I had the ability to zoom in, as x goes towards infinity, that is, as x gets really large over here, the value of my function would get closer and closer to this line. As x gets infinitely large, negative, the value of my function, so x is getting larger and larger but negative, the y value approaches 0. Then it gets really, really small. But will it ever be 0? No. It just approaches 0. So this is the concept, the beginning concepts of a limit. A vertical asymptote. The value of the function f of x approaches infinity, or f of x approaches negative infinity, as x approaches some constant c. So where c is a constant, note that vertical asymptotes are vertical lines and thus have the equation x is equal to c. I'm going to revisit this first graph again. What I notice is that I have two vertical asymptotes. And the definitions I kind of understand are a little bit tough. But what we say is that the value of my function either gets really large, the y values either get really, really large in the positive direction or really large in the negative direction as x goes towards some constant c, where c is just any number. Let's look back at our graph here, graph number 1. Now, by the way, this x value down here is 2. So what I'm going to say here, as x goes towards 2 from the positive side, that's a weird thought. Here, I'm going to approach where x gets closer and closer to 2. Where's my eraser? I got to find it. There we are. As x gets closer and closer to 2. So x is over here, and it gets closer and closer to 2 from the positive direction. What happens to the y value? The y value gets incredibly high. And the closer you are to 2, the y value gets increasingly large. How large? Incredibly large. However, on this side over here, this is going to be weird for you as x approaches 2 from the negative side. That is, when I approach 2 from this side, my y value gets extraordinarily large and negative. Now, basically, I like to think vertical asymptotes is almost like a force field where your function goes boom or boom. You can't cross a vertical asymptote, and there's good reason for that, but your function will deflect either all the way up or all the way down. And when I say all the way up, I mean all the way up to as it approaches positive infinity. If you are having a hard concept with x approaches 2 from the positive side, think of this. There 2 is positive, or sorry, 2 is higher than 2. That's approaching 2 from the positive side. If you approach 2 from the negative side, you're looking for a number that is incredibly small, incredibly close to 2, but just a little bit smaller than 2. So we can say we approach positive 2 from the negative side, approach positive 2 from the positive side. And I know this vocabulary is all really new to you, but it starts to make sense after a while. All right. So what do I want you to take away? I would like you to take away from this, whereas right now, wow, rational functions look tricky. Okay, they're not really. They're delicate. But we have to get these asymptotes down. In order to understand the function and the behaviors of the functions, we need to understand the asymptotes.